Okay, so we're still talking about Ramsey theory, and we would where we left off is that we would like a lower bound on R of ST. And let me just go back to the definition to talk about what a lower bound actually means. What we would like is to show that for some value of n, that it does not have this property, that there exists a red-blue coloring of the edges of Kn that does not contain any blue Ks or a red Kt. So that's what we're going to try to do. And yeah, so this takes us through kind of a strange detour. What we're going to do is we're going to consider a random coloring, where you could imagine literally flipping a coin for each edge of Kn to determine whether it's red or blue. And we're going to consider that coloring of the edges. And then, in some sense, we're going to show that there's a... Okay, I'm lying a little bit when I say this, but we're going to show that there's a decent probability that when you do that, you don't have any blue Ks or a red Kt. And that demonstrates the existence of such a coloring. Just stating that if you do it randomly, you have a decent chance of producing a coloring with the property that you desire. That shows the existence of such a coloring. It's a bit strange that the only way we can do that is by talking about a random coloring. It's strange that we can't just show specifically which coloring has that property, but sometimes math is strange. Okay, so basic probability theory. Probability theory is a difficult subject that gets pathological at times. We are not going to touch any of that stuff. We are going to do basic probability theory. So for us, a probability space is just a pair consisting of P and omega, where omega is a set. For us, it's going to be always finite. That's one of the simplifying things. That's why the probability theory we talk about is so simple. Omega is going to be a finite set. P is your probability function. It goes from omega to the interval from 0 to 1, and of course that we assume that if you add up all the probabilities of all the possible things in omega, that's 1. The elements of omega, these lowercase omegas, sometimes I call these outcomes. So the sum of all possible outcomes has a probability of 1. A random variable is a function. Typically, these functions are denoted with a capital letter x from omega to the real numbers. And the expected value of a random variable is this. It's the sum over omega of the value of x times the probability of that outcome, p of omega, which what this really is, it's like a weighted average. You can think of this as a weighted average. These p of omegas, they're a bunch of numbers that add up to 1. And what we're doing when we take this sum is we're taking a bunch of values of this function and I'm multiplying each one by its own number, and these coefficients, the p's, those all add up to 1. So in that sense, this is a weighted average, and each possible outcome is weighted according to its probability. So, couple of facts about expectation. And yeah, by the way, when I say expectation, that's synonymous with expected value. If you take any two constants, a and b, the expected value of ax plus by is just, it's what you get if you, basically, this is a statement of the fact that you can separate out addition and you can also pull out constant multiples. So I can take this expectation and just do the expectation of each one, and I can pull the A outside of this one and the B outside of this one and get this. This is called linearity of expectation. The proof of this is easy. Just go up here and literally just plug this in, like so instead of x, you'll have ax plus by, and then we know that we can pull constants out of sums, and I know that I have the distributive property. So if you plug it in here and then take that sum apart, you will get this. So that proof is pretty much by definition. Here's another fact about expectation, and this one I would call the basic classical probabilistic method. So the fact is, for any probability space and any random variable in that probability space, you always have that there exists a little omega such that x of little omega is greater than or equal to the expectation of x. This is really, it's an intuitive fact based on the fact that the expectation of x is a weighted average, and it's not possible for all of these to be smaller than their weighted average. There has to be something bringing that average up. So there's a similar fact, of course, where there exists an omega such that you have the reverse inequality. Anyway, let's go through the formal proof. And the formal proof is kind of just, it's a formalization of the intuitive idea that I just said. Suppose it was the case that for all omega, and this is a proof by contradiction, and I'm just writing the negation of this. So for all omega, we have x of omega is strictly less than this. Well, then look, this is defined to be this, and if this is always less than this, then I can write this inequality. But then, now I'm looking at this, expectation of x is a constant, so this can pull out in front, and if I pull that out in front, then I'm just summing up p of omega for all omega, and I know that that sum is 1. That's this, right? If I pull e of x out, then I'm just summing up p of omega, and that sum is 1, so, you know, I can write times 1 here if you like, but this equals the expectation of x. So we just showed that the expectation of x is strictly less than the expectation of x. This argument is literally just a formalization of the idea that something has to be bringing the average up in order for the average to be so high. You can prove this one by just reversing all the inequalities. Okay, so that is basic probability theory. So let's use that to show the following lower bound on Ramsey numbers. I'm going to do the so-called diagonal Ramsey numbers. If you recall, sorry, I have to sneak this in here. When S and T were the same, like say R of KK, we just call that R of K. So I'm going to focus on that case, but we're going to show a lower bound on it. So the lower bound that I'll show is 2 to the k minus 1 over 2. And this is true for all k greater than or equal to 3. So here's the proof. Again, sorry for all the scribbles, but what do we have to do for this? We have to show, once again, we are doing a lower bound on a Ramsey number. So I have to show that for some value of n, it does not have this property. The way Ramsey numbers work is some values of n have this property and some don't. And there's a transition point where you have a bunch of small values of n that do not satisfy this property, and they're all in a row, they're all consecutive, and then suddenly you'll have one value of n that does satisfy this property, and then after that every value of n satisfies this property. And then of course the Ramsey number is the smallest value of n that satisfies this property. So what I have to do to show a lower bound is to show that there's, to show for some value of n that it does not satisfy this property, and that's a lower bound on R of st. So suppose n is less than or equal to this. I'm going to show that for such a value of n, there does exist a coloring. In other words, I'm showing that this value of n does not have the property. In other words, if I negate this, I get that there exists a red-blue coloring of the edges that does not contain a blue ks or a red kt, where s and t are both k. And I do that by considering a random coloring. And when I say random, I mean every edge is either red or blue with probability 1/2, and this is independent. So whether one edge is red or blue, that doesn't affect the probability that another edge is red or blue. It's still a probability of 1/2. And let's let the random variable x be the number of things that we don't want to see. What do I not want to see? I don't want to see any entirely red k sub k's or blue k sub k's. And when I say monochromatic, that just means all one color, whether it's red or blue. So I don't care whether it's red or blue. I just care if it's all the same color. I don't like it. So that's what x is. So we have our probability space. Our probability space is all possible colorings, all possible red and blue colorings. And they're all equally likely because of the way we're doing it. We're coloring every edge with red or blue with probability 1/2 independently. So any coloring is equally likely. And x is the number of monochromatic k sub k's. So I would like to find the expected value of x. And in order to do that, I'm going to rewrite x as like sort of just a literal interpretation of what it's counting. X is counting the number of monochromatic subgraphs. So here's how I can write x. I can do a sum over all sets of k vertices. And I have this funny looking thing written in here, this bold-faced 1 with a subscript. A bold-faced 1 with a subscript just means it's either 1 or 0. It's 1 if the subscript is a true statement, and it's 0 if the subscript is a false statement. So let me go back to this. I'm going to add up for every set S of k vertices. And what I'm going to add is either a 1 if that set is a monochromatic set, meaning all of the edges among vertices in that set are the same color. I'm going to add a 1. Otherwise, I'm just going to put a 0. And if you think about it, I mean, you don't even really need to think about it. If you add all of this up, you're going to have a bunch of zeros plus a bunch of 1s. How many 1s do you have? The number of 1s you have is the number of monochromatic sets, and that's what we were trying to count. So, of course, x is this. And writing it this way makes it easier to find the expectation of x. So now, the expectation of x, because we have linearity of expectation, it's like I'm just doing the expectation of both sides of this, and when I do the expectation on the right, I can pull it inside the sum because of linearity of expectation, because of, yeah, this. So I can pull it inside the sum, and when you're doing the expectation of one of these things, and by the way, these things, these bold-faced ones, these are called indicator variables. It just indicates whether the subscript is true or false. It indicates that it's true by saying it's 1, and it indicates that it's false by saying 0. These are called indicator random variables. The expectation of such a thing, well, let's think about what expectation is. Expectation basically runs through every possible outcome, and it weights outcomes by their probabilities. So there's 2 possible outcomes of this, because this is an indicator random variable. It could be either 0 or 1. So let's look at all the times that it's 0. It's 0 with this probability. That's just the probability that E doesn't happen, right? An indicator variable returns 0 whenever the subscript is not true. So this is the probability that the subscript is not true. That's the bar over it is the complement. Of course, none of that matters because it's times 0. But anyway, the other outcome is that the indicator variable would be 1, and that's the and that happens with this probability. And this is the term that does matter, so in the end, we just get the probability of E. So what I'm telling you is that the expected value of an indicator random variable is just the probability of the event that's written in the subscript. So the expected value of this indicator random variable is just the probability of the event that's written in the subscript. So then we're there. Now we just say, first of all, I'm going to evaluate this sum. The number of terms in this sum is just n choose k, because there's a term for every set of k vertices. So the number of terms is just n choose k. And then, so there's that many terms, and then what is each term? What's the probability that S is inducing a monochromatic set? In other words, out of these k vertices that we're calling S, that all of the edges are the same color. I claim that that probability is this. The 2 is there to choose which color, whether it's red or blue. And then, so suppose we've determined a color, and now we're saying what's the probability that all of the edges are blue? Well, we're flipping a coin for each edge. So the probability that one edge is blue would be 1/2. The probability that they're all blue, because we have k vertices and the number of edges among those vertices would be k choose 2. The probability that they're all blue would be 1/2 to the k choose 2. And of course, the probability that they would all be red is also 1/2 to the k choose 2. Okay, so that's that. And now I'm just going to use a couple of inequalities. So first of all, yeah, maybe I'll just make a bubble here. N choose k, one way of writing n choose k is it's n times n minus 1 all the way down to n minus k plus 1 over k factorial. And that's less than or equal to n to the k over k factorial, right? Because the numerator, I'm multiplying a bunch of numbers. How many numbers? There's k of them. If you count, this is 1, 2, 3, and this would be the kth one. And all of them are less than or equal to n, so the top is less than or equal to n to the k. So that's just a simple inequality for n choose k. So I used that inequality, and that's what we got here. And then just remember about our value of n. Our value of n was less than or equal to this, 2 to the k minus 1 over 2. And so, yeah, maybe I should really sneak in another thing here. This is 2 over k factorial. N is like 2 to the k minus 1 over 2. But this was n to the k. And then I have this 1/2 to the... Yeah, sorry, this is probably going to turn out poorly, but I have 1/2 to this power, and I'm pointing out that this perfectly cancels out with this, right? It's 2 to the k times k minus 1 over 2, and that's exactly what we have in the denominator because of that one. That's why this is less than or equal to 2 over k factorial, and since k is at least 3, that's smaller than 1. Okay, so what just happened? We showed that the expected value of x is less than 1. So because of this, there exists an outcome such that x of omega is less than or equal to this. This is smaller than 1. So there exists an outcome such that x, in that outcome, the value of x is less than 1. It's strictly less than 1. What we're talking about is counting the number of monochromatic k sub k's. And that's an integer. And it's a non-negative integer. No matter what it is, it's a non-negative integer. So if we're talking about an outcome where that is less than 1, that means it's 0. So, yeah, actually maybe I should make this more clear in the notes. There exists an outcome where that's less than 1, which means there's only one value it could be because it's a non-negative integer, so it must be 0. In other words, there exists an outcome where there are 0 monochromatic k sub k subgraphs. In other words, you don't have any red set of size k vertices or blue set of size k vertices. And that's it. So, right. We did it. So, the crazy thing is the amount of effort that's been put into estimating Ramsey numbers, and the fact that out of the upper bound and lower bound that I've shown you today, those are basically the best known in some sense. That's not exactly true, but I'll explain. If you look at the best known, say, upper bound, it's, well, so first of all, let's look at the upper bound we proved. The upper bound we proved is that r of st is less than or equal to 2 to the s plus t. So if we were talking about r of k, that just means that these are both k. We would get 2 to the 2k. So the upper bound that we showed was 2 to the 2k. The best known upper bound is not much better than that. It's still essentially 2 to the 2k in the following sense. The best known upper bound can be described like this. I can put 2 to the, and then parentheses, 2 plus this little o of 1 thing times k, where this little o of 1 is replacing some function that goes to 0 as k goes to infinity. It would be nice for example, to know that r of k is less than or equal to, say, 2 to the 1.9999999k for all k. It's not known if that's true. And so in this sense, even the best known bound, it's not essentially improving this number. It's not essentially improving this 2. This would be essentially improving the 2. And when I say essentially, I mean, of course, as k goes to infinity, this is essentially still 2 to the 2k. It's very close to 2 to the 2k. And by the way, this bound was improved very recently by Ashwin Saw. Like the paper's probably not even really refereed yet, but I believe it because he's a really smart guy, and he's a very young guy too. He might be like your age. Anyway, it's a similar story on the lower bound. On the lower bound, it's essentially 2 to the 1/2 k. And that's also sort of what we proved. We showed that the lower bound, k minus 1 over 2. And as k goes to infinity, this 1 is negligible compared to the k. So as k goes to infinity, I would describe this as essentially 2 to the k over 2. And that is, again, essentially the best known, despite a lot of effort. And here the best known bound has not been improved in many years, I think since maybe the 70s. The best known bound is somewhat better than the one that we showed, but not in a meaningful way, at least in the sense that we also don't know this. You know, it would be nice to know that r of k is greater than or equal to, say, 0.50000001 k for all k. If anybody proved either of these, they would be very famous. They could get a very good job and probably not have to do anything else for a long time. just living off of that one success. Anyway, yeah, that's the state of things.